We'll now look at the next layer in the atmosphere, called the stratosphere. This layer is characterized by the lack of any significant change in temperature with height. The stratosphere stops when temperature starts to decrease with height again. At this point, we find the upper boundary to the stratosphere, which is called the stratopause. This is usually found at about 50 kilometers above the surface of the Earth. The temperature of the stratosphere can rise a little in the upper levels due to the presence of ozone gas. But further explanation on this is outside the scope of the learning requirements. Returning to our image of the Earth, you can now see the stratosphere and stratopause. There are several more layers to the atmosphere, but these are outside the learning requirements for the private pilot's license, and will therefore not be considered. Before we leave the structure of the atmosphere, there is an important point to make about the tropopause that is significant to a pilot. We stated that the tropopause was where temperature no longer decreases with height. This causes air to become very stable. In other words, it limits the vertical movement of air. This lack of vertical airflow prevents any further cloud development, and therefore the tropopause signifies the limit of the majority of weather and significant cloud development. For many purposes, such as calibrations of instruments and testing of aircraft, an average state of the atmosphere needs to be represented and modelled. This is called a standard atmosphere. In 1964, the International Civil Aviation Organization, ICAO, defined the properties of this average standard atmosphere, and this is referred to as the ICAO Standard Atmosphere, which is abbreviated to ISA or ISA. However, the model only extends to 32 kilometers, which is about 105,000 feet above mean sea level, so the entire atmosphere is not considered. ISA assumes that at mean sea level, the temperature is 15 degrees Celsius, pressure is 1013.25 hectopascals, and the density is 1.225 kilograms per meter cubed. From mean sea level to 11 kilometers or 36,090 feet, the temperature decreases by 1.98 degrees Celsius per 1,000 feet or 0.65 degrees Celsius per 100 meters. From 11 kilometers to 20 kilometers, the temperature remains constant at minus 56.5 degrees Celsius. Notice that at 11 kilometers, the temperature no longer falls with height, and therefore marks the top of the troposphere. You may remember that we called this point the tropopause. The layer above this was called the stratosphere. From 20 kilometers to 32 kilometers, the temperature rises slowly at 0.3 degrees Celsius per 1,000 feet or 0.1 degrees Celsius per 100 meters. ISA is only one of several types of standard atmosphere, but it is the most recognized and the most familiar of them all. Since all aircraft instruments are calibrated in accordance with ISA, it is essential to know how much the actual atmosphere on a given day differs from ISA. This will help quantify errors and improve the accuracy of the readings from these instruments. The simplest method we use to analyze this difference is by comparing the real temperature to the standard ISA temperature. This comparison gives us what is known as the ISA deviation. In other words, by how much does the real atmosphere deviate from the standard atmosphere? Let's work through an example to help understand this principle. In the diagram, we can see an airfield 1,000 feet above sea level. Remember that in ISA, we stated that mean sea level temperature was 15 degrees Celsius, and then falls by 1.98 degrees Celsius per every 1,000 feet up to 11 kilometers. For simplicity, let's assume it is 2 degrees Celsius per 1,000 feet. Therefore, The temperature at 1,000 feet, according to IS